Right, section 4.6, the fundamental theorem of algebra. Our objective for this lesson is to use the fundamental theorem of algebra, find conjugate pairs of complex zeros of polynomial functions. Okay, so this is really going to be a continuation on 4.5. Don't worry, it's not going to be as long as the 4.5 video is. Okay, but it basically is just a continuation of that, and we're just going to step it up one little notch. If you notice in section 4.5, all of our solutions were real numbers. Okay, remember we have two different sets of numbers. We have the real numbers, again, which consist of all of our real numbers like 4, negative 1/3, also 2 plus root 5, that's a real number. But then we also had our complex numbers. Okay, our complex numbers. Okay, the real numbers are a part of the complex numbers, but the complex numbers has another section, and that includes our I numbers, our imaginary. Okay. So we were just finding solutions in the real numbers. We weren't doing any imaginary yet. Now we're going to include our imaginary numbers. Okay, so first let's look at a bit of a pattern. Okay, so here if I look at this equation, 2x minus 1 equals 0. If I look at the degree of this equation, the degree of this equation is just x to the 1. The degree is 1, which makes it a linear equation. And if I was to solve this, I'm not going to go through the process of solving it, but if you solve it, you get a solution of 1/2. When I put a 1/2 in this for x, it makes this equation true. So it only has that one solution. There's only one number that will make this equation true. Okay, so now here this next one, x squared minus 2 equals 0. Okay, if I solve this, well first let's look at the degree. The degree of this is 2, which means it's a quadratic. That's the name of it. It's degree of 2. If I was to solve this, we'd add the 2 to both sides, square root, we get a plus or minus. So I end up getting a solution here, positive root 2 and negative root 2. So this actually has two different solutions. We just write them together. This really means a solution of root 2 and negative root 2. Two arrows there. A positive root 2 and a negative root 2. So this actually has two solutions. Okay? All right, if we look at this next one, x to the 3rd minus 8. If we solve this one, add the 8 to both sides, cube root both sides. If we solve this completely, and actually to solve this, I would probably factor it using our difference of cubes, which we just learned. Okay, but this is degree 3, which we call a cubic. Okay, but if we solve it, these are the solutions we get. If we're looking at all the solutions, we get a solution of 2, a negative 1 plus I root 3, and a negative 1 minus I root 3. So this ends up having 3 solutions. Okay. All right, same with this one. This one is a degree of 3, also a cubic. And when I solve this, factor it and solve it all out, I get these solutions. Negative 1, which again, remember from our last section, negative 1 is the solution multiplicity of 2. So it happens twice in the one. But if we count each one as its own separate solution, it has 3 of them. If you notice, degree 1 equation has 1 solution, a degree 2 equation has 2 solutions, a degree 3 equation has 3 solutions. So what do you think if I had a degree 4 equation, how many solutions do you think it's going to have? Yeah, 4. That's a nice little pattern there. So if I had an x to the 4th blah, 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 blah equals 0, okay, it's going to have 4 solutions. Okay, so this is really the fundamental theorem of algebra. Okay, this was a very big theorem back in the day. It's useful, but it's more of what we call an existence theorem. It tells me something exists. It doesn't necessarily tell me how to find it. Okay, it tells me that these solutions exist. It doesn't tell me how to go about finding them, so we'll have to use a bunch of our different skills for that. Okay, so here's the theorem. It says if f of x is a polynomial of degree n. So degree, here's my degree 1, 2, 3, 4, where n is greater than 0. So we only have positive degree equations. If you notice, we don't have a degree of like negative 2. That's for later in the year, okay? Then the equation f of x equals 0 has at least one solution in the set of complex numbers. So in the set of complex numbers, which includes the imaginary, basically what that tells me is any polynomial of degree greater than 0, 1, 2, 3, 4, okay, is going to have at least one solution. Okay, at least one. Okay. We can actually take a corollary. If you remember from geometry, corollary is basically just another little theorem it's another piece that can be proven off this theorem. And this goes even farther to say if f of x is a polynomial of degree n, again, where n is greater than 0, so we don't have any negative degrees, then the equation f of x equals 0 has exactly n solutions. Then the equation f of x has exactly n solutions, provided each solution that is repeated counts. So if something happens 3 times, it counts as 3 zeros. So what that tells me, if I have an equation x to the 5th equals something, and it's degree 5, that tells me this thing is going to have 5 solutions. Okay, so it helps me know whether I found them all or not. Like, did I find all of the solutions? Did I just find some of them? Okay, so let's go through the process of finding all the zeros of a polynomial equation. So first step is I want to find all the zeros of this polynomial equation right here. So it's x to the 5th. So this tells me here it's degree 5. So I know it's going to have 5 solutions. So when it's all said and done, I need to have 5 of them. Okay, I'm always looking for, is there some way I can factor this or something? If we look, it's got 1, 2, 3, 4, 5 terms, so grouping probably won't work because I can't group 2 and 2. So I'm going to resort to the stuff from the last section. I'm going to kind of do that P over Q. I'm going to come up with my P's over Q's so I have a place to start, and then we'll use our calculator to find the rest of them. Okay, so my P's come from my constant term right here, my 8. So my 8, the factors of 8 are 1 and 8, 2 and 4. So those are my P's. My Q's come from the leading coefficient here, which is a 1 in front of that, x squared. So 1 is just 1 and 1. So now I take each of these and put them over there. So 1 over 1 is 1, again plus or minus. 2 over 1 is 2. 4 over 1. And 8 over 1. Okay, so this gives me, it's actually 8 numbers to try. 1, 2, 4, 8, negative 1, negative 2, negative 4, negative 8. Okay, so now what I'm going to do is I'm going to go into my calculator, go into my y equals, and I'm going to type this into my y equals to check some of these points. So x to the 5th plus x to the 3rd minus 2x squared minus 12x minus 8. So let's double check, make sure. If neat trick, second left arrow gets you all the way back to the beginning. X to the 5th plus x to the 3rd minus 2x squared minus 12x minus 8. Okay, let's go to the graph. Okay. And we're going to check these points. So it looks like maybe negative 1. Trace. Negative 1. Yep, negative 1 got me a 0. So I know negative 1 is a 0. X equals negative 1 is a solution. So if x equals negative 1 is a solution, x plus 1 is a factor. So now I'm going to synthetically divide by this x plus 1. So do negative 1. So we have 1x to the 5th. We don't have any x to the 4th, so I'm going to need a 0 placeholder. 1x to the 3rd, negative 2x to the 2nd, negative 12x, negative 8. So 5, 4, 3, 2, 1 constant. Okay, bring down the 1. Negative 1, 1, 2, negative 2, negative 4, 4 gives me 4. Negative 8, 8 gives me 0. Okay, so I have x plus 1 as a factor. So now my other factor is this guy here, and it's always, again, always 1 degree less than that. So this is x to the 5th, so this would be x to the 4th minus x to the 3rd plus 2x squared minus 4x minus 8. Okay, so this is still x to the 4th, which again, I can't use a quadratic formula. Our end goal is we want to get it down to an x squared. Because an x squared is quadratic, and if all else fails, so we want to get it down to an x squared. An x squared is quadratic, and a quadratic we can either factor it, complete the square, or quadratic formula it. quadratic formula it. Okay, so that's our end goal. Right now we're only at x to the fourth. So we need to keep going. We need to see if there's any others. Well, if you notice, I've got this one here. 1, 2, I think it's 2. Let's trace 2. Yep, 2 is a 0. So we're going to keep going. So x equals 2 is also a 0. So that means x minus 2 is a factor. So now we're going to divide again. We're going to divide by negative 2. Oh, sorry, positive 2. Remember, we got to switch a sign. So it'll just be the 2. Okay. But we're not going to start back at the beginning. We already have it factored down. We have it factored down to this. So we're going to use that guy. 1, negative 1, 2, negative 4, negative 8. All right, let's synthetically divide. 1, 2, 1, 2, 4, gives me 8, 4, 8, 0. Okay, so now I have this factor from before, this x plus 1. Now I have this new factor, this x minus 2. And then now we have this factor, which is going to be 1 less than this. This one wasn't, we started with an x to the 5th. I divided once, gave me an x to the 4th. We divide again, that's going to give me x to the 3rd plus x to the 2nd. That's 4x. It's 4. Okay. And then now we want to look. So now I have an x to the 3rd, but I've got 4 terms. Okay, so I could either go again, look for another one, which I only see the 2, but the fact that this comes off and bounces off at negative 1 tells me that that multiplicity is even. Remember from our last section, if it just bounces off, it has an even multiplicity. So that tells me that this negative 1 probably is going to work again. So let's go ahead and let's try the negative 1 one more time. Okay, so we're going to divide by that negative 1 again. But again, don't start from scratch. Go back to this one we have here. So I'm going to use the 1, the 1, the 4, the 4. Okay, from this guy right here. Okay, so bring down the 1, negative 1, 0, 0, 4, negative 4, 0. Okay, so then I had an x plus 1, but now I've got 2 of them. So this is going to be x plus 1 quantity squared, x minus 2, and now what's left? An x squared plus 0x plus 4. Again, this still equals 0. So I know the zeros for this. It's going to be the negative 1 and the negative 1. So our zeros end up being here. We've got our negative 1, and our 2. Again, remember, we have to have 5 solutions. We've got 3. 1, 2, 3. And the 1, 2, 3 come from this guy. There's the 2 of them. The x equals negative 1 with a multiplicity of 2. This one's got the x equals 2. So now all we need to find is the zeros of this guy. So I need to figure out what makes this guy equal to 0. So x squared plus 4 is equal to 0. I'm going to subtract the 4 from both sides. And then square root both sides. So x would equal, when I square root both sides, that's plus or minus. The square root of negative 4, the square root of the negative is I. The square root of 4 is 2, so 2i. So I've got negative 1 and negative 1. That one happens twice. 2i, and negative 2i. So now I'm going to list my solutions. I should have 5 of them. I'm going to list them all. Negative 1, 2, and then we had 2i and negative 2i. So I know it's going to have 5 solutions. I know it's going to have 5 solutions. I found them all. 1, 2, 3, 4, 5. Okay. All right. Just have one more little bit, then we're done. Okay. The complex conjugates theorem. If you remember from the previous section, we said if a plus square root of b is a solution, then a minus the square root of b is also a solution. This just extends, the complex conjugates theorem just extends this to imaginary. If a plus b is an imaginary solution or 0, then a minus bi is also. Okay? So basically it's that same process, it just extends it to the i's as opposed to the rationals irrationals with the square roots. Okay? So here for this example, we want to write a polynomial function f of least degree that has the rational coefficients, so nice rational numbers, a leading coefficient of 1, the smallest one possible, and zeros 2 and 3 plus I. Well, since complex zeros come in conjugate pairs, if 3 plus I is a solution, 3 minus I also is. You notice the first number doesn't change, it's just the sign in the middle. Okay, so basically we're starting at this point here at the end, and we want to get back to this beginning, back to where we started right here. So I know I have three different solutions. I have a solution of x equals 1, x, oh, sorry, not 1, 2. The zeros of 2, 3 plus I, and x equals 3 minus I. Okay, so if those are my solutions, then x minus 2 is a factor, x minus 3 plus I, and then x minus 3 minus I. So we simplify this here. Sorry, crooked. We'd get x minus 3 minus I when I distribute that negative in. X minus 3 plus I. And now I just need to multiply this guy, which he looks a little bit weird, but kind of like with that last one, if I multiply these two I things first, it actually simplifies really nice. So we'll leave this x minus 2 out front. Multiply this guy. X times x, x squared, minus 3x, plus ix, okay, minus 3x, plus 9, minus 3I, minus ix, plus 3I, minus I squared. Okay, the whole thing. All right, like terms. I've got a positive ix right here, a negative ix, minus 3I, positive 3I. And if you remember, I squared is equal to negative 1. So this guy is negative 1. So we have subtracting a negative 1. So when we put like terms together, we'd have an x squared, that guy, minus 3x gives me minus 6x, plus 9, minus a negative 1 gives me plus 10. So there, that's how it simplifies. And if I was to find the solutions of this little chunk here, I would get 3 plus or minus I. Meaning if I was to take this and branch it off and find the solutions on where this equals 0, I would get dot, 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 dot. If I use the quadratic formula, I'd end up getting x equals 3 plus or minus I to get those two. Hey, now I just need to distribute one more time. X to the third minus 6x squared plus 10x minus 2x squared plus 12x minus 20. So my function f of x, and because it says function f up here, function f right there. Hey, I have x to the third, take care of that guy, minus 6x squared minus 2x squared negative 8x squared plus 10x plus 12x plus 22x minus 20. So there's my function. If I was to solve this one, I would get these three solutions. And we know it has three solutions because it's an x to the third. It's degree of 3. Which tells me it's going to have three solutions. Okay, good luck with 4.6.